Okay, let's see if this happens. Today we're going to start with strengths of acids and bases. So first we're going to be defining what a strong acid is and what a weak acid is. And where can you find a list of the strong acids? On your periodic table. And if you'll double check those right now, you'll see that there are 6 of those. I don't know why it tells me I'm starting my session. Then I've got to get over to my next one. We're going to describe how an acid's strength is related to the value of its acid dissociation constant, which is its Ka. We're going to learn to calculate the acid dissociation constant from either concentration and or pH measurements. Pretty simple. We'll order acids by their dissociation constants. And remember, the smaller K values, in this case Ka, will have less dissociation. Okay, there's that one. Okay. Acids and bases are just classified by how they ionize in water. And they ionize as follows. Strong acids are ionized completely. That means they have 100% dissociation. And if we consider an acid to be HA, that means it dissociates completely into H pluses and A minuses, where this is your hydrogen ion, obviously, and that's your associated anion. And the 6 that do that are on your periodic table. Weak acids, on the other hand, most of it doesn't dissociate. Most of the acid remains as a molecule. Strength is very different than concentration. Strength refers to degree of ionization, and concentration is usually in units of moles per liter. That'd be the most common. Sometimes it's moles per kilogram of solvent, but usually it's listed as molarity. And here's something to consider. Acetic acid is perhaps the most common weak acid. It's ethanoic acid, acetic acid. It is CH3COOH. So it's a weak acid because it's got this carboxylic acid group. I can have 1 molar hydrochloric acid, which is a strong acid. I can have 1 molar acetic acid. The difference will be in how much H plus I have available. The HCl will have 1 mole of H plus available. The weak acid, the acetic acid, will have much less because most of it remains in the molecular form. Again, this is something we already had. Strong acids, 100% ionization. This acid, actually, if you'll double check your periodic table, is not on your list as strong. It says it's a strong base. It falls completely apart when dissociated. And this one's sort of interesting because it is an Mg2 plus and 2 OH minuses. You can see that it's got the 2 OH minuses. But not much dissolves, so it's not very concentrated. So this would have a low KSP. The bases are a little bit harder to figure out, but we don't have to worry about them. Just look at the strong acids as those that are listed on your periodic table. I don't know why this is telling me to slow down a bit. I love this slide because it shows us a strong acid dissociation. So let's just pretend that this is 1 molar. If I have 1 molar of a strong acid, HA, it'll dissociate into 1 molar H plus, which is this, and it'll dissociate into 1 molar A minus, which is this. 100% dissociation. Here's our dissociation equation. You'll notice that that's a one-way arrow because it's like completely dissociated. Here we have a two-way arrow, and this one, whoever did this did a nice job on it because they said most of it stays in the molecular form. If this is my original concentration, let's say it's 1 molar, after it dissociates, and this is just an abbreviation, I'd have like 0.9 molar here and 0.1 and 0.1. Because in a weak acid, a very weak acid, a very small amount dissociates. Easy peasy. Ionization can be reversible, and I don't love this equation because you'll notice there's not an O on each side, so I could make this look a little bit better by doing H3, whoops. Oh no, where's my eraser? I don't know where my eraser is, so I gotta start over. HA plus H2O this would be H3O plus A minus. Remember, in our world, H3O plus is equal to the H plus concentration. We can use those terms interchangeably. This is an equilibrium, and if I was to write my dissociation constant for this, we would write this because this is an L, all the others are AQs. So our Ka expression, and remember Ka is for acids, it's just a special kind of K, specifically for acids. And for this one, our products are on the top over our reactants in the denominator. You should be very familiar with those. A stronger acid will have a larger Ka. For instance, think of an acid with a Ka of 10 to the minus 8th and another acid with a Ka of 10 to the minus 4th. This would be the stronger acid because this is a much larger number than 10 to the minus 8th. Everybody knows that when I say it, but it's sort of hard to remember because when you see that 8 versus the 4, it's easy to say, oh, the minus 8 is bigger than the minus 4. But if you stop and think about it, you know that's not true. Does that make sense when I say that? It's an easy mistake to make. Bases, if they're strong, also dissociate completely, and they dissociate a little differently. M stands for metal, so a metal hydroxide, this is what we're most used to, dissociates as you see following. And I like to write these just as MgOH, and it just breaks down into this, and leave my water off. Again, we can omit the water from our Kb expression because it's a liquid. So here would be my Kb expression. So Ka is for acids, Kb is for base. Easy peasy, lemon squeezy. Just like acids, the stronger base means that more dissociated ions are produced because it has a larger Ka. So the larger the Ka, the more OH are produced. And that's pretty simple. It's the exact same concept as Ka. It's just for OH minuses instead of for H plus. Okay, so this is just more the same thing. You can read that. Here is one of my favorites to look at. We'll use this a little bit later today, but this is a very good example of a weak base dissociation, and we'll practice that one in a moment. Okay. The same concentration of water, base dissociation constant, conjugate over the base, and that. I don't really want to look at these too much. Here's just a few acids and bases and relative strengths. And these three were on our list for strong. And these, I think these three were on our list for strong. So all of these in here are weaks. Okay, this is where I wanted to get to. Concentrated and dilute. For an example, I might have a concentrated solution that was 1 molar HCl. And a dilute solution would be like 0.1 molar HCl. This would be a strong. They're both strong acids. This strong acid solutions. I might also have 1.0 molar, and I'm going to go like this for acetic acid, or 0.1 molar acetic acid. Again, we have a concentrated and a dilute, and this is for a weak acid. The words strong and weak talk about the extent of ionization, and the words well, that's not going to be on there. Is it possible to have a concentrated weak acid? What do you think?
Yes.
It is. Okay, there's just some more. There's strong, strong. And we've got concentrated, dilute, concentrated, dilute. So you can have any combination. Excuse me. Writing the Ka expression for HNO2. This is a weak acid because it's not on your list. So when this dissociates, it's going to dissociate as follows. Please note the double arrow, H plus and NO2 minus. This is the first step. Whenever you're writing any of these, I always start by writing out my equation. Then the next step is I write out my Ka expression. So there's the Ka expression. Don't forget, the biggest mistake is products over reactants. So there's our Ka expression. And that should be familiar with everybody. Does that look familiar to everybody? Something that's not too hard to do? This one's a little bit different, and I sort of skipped over this quickly here. If I have NH3, I'm going to add this one to H2O, and this is going to dissociate into NH4 plus and OH minus. And this is the only L. These three species will all be aqueous. We'll get more practice with this. It's a little bit tougher to draw or to write the information for ammonia because it is not an arrhenius acid. This is a Bronsted-Lowry acid, or Bronsted-Lowry base, excuse me. Oh, this is hard to read. Not too bad, though. So this tells us that we have 0.100 molar solution of ethanoic acid. This is an ice problem, so you guys can probably see this pretty well here. But you can see I've got my initial change and equilibrium, my initial change and equilibrium, and this is 0.10000 and 0. So for right now, does everybody see where those three values came from in the ice world of ice? And we're also told that it's partially ionized, and it tells me my H plus concentration, this is hard to read, at the end, this is my equilibrium, is equal to 1.34 times 10 to the minus third molar. And that's where this number comes from. That is 1.34 times 10 to the minus 3 molar. Based on my coefficients in my dissociation equation, which is right here, I have a coefficient of 1, 1, and 1. I know that these two values have to be the same. This is plus x. This is plus x. This will be minus x. We've subbed these into our value, and you guys can satisfy your own curiosity on this. I get 1.82 I think that's 10 to the minus 5. I can't read it. Or maybe it's 10, minus 10. I can't read that. So I would have to get somewhere else and look at this one. Let me see if I can pull that up, because I was showing this earlier on my computer. 10 to the minus 5. 1.82 times 10 to the minus 5. So 1.82 times 10 to the minus 5. And this is an easy ice. So on this problem with this ice work, the only difficulty here is making sure you know what your change row is going to look like. And for that, we have to take a look at everything we're given in the problem. And this is what our guided practice is going to be today. One thing I'd like everybody to do right now, have you guys got your calculators out? I'd like you to recalculate this, and instead of 0.0987 in the denominator, just use the 0.1000 and see what you get. So you're going to take 1.34 times 10 to the negative third squared, square that, and then divide it by 0.1. And tell me what you get when you're using
1.79 to the negative fifth.
Let's round that to 1.8 times 10 to the negative fifth. Now, when we get that number, the 1.8 times 10 to the minus fifth, notice it's very close. Does that make sense? Because this value, and we'll look at this more when we do our guided practice in a few minutes, dividing this by 0.1 or dividing it by 0.0987 is going to have very little impact on your answer. And that's going to be something that you'll find out is valuable in about 2 minutes. Okay, I think that's all I have to do on this slide. Okay, we already have that. Okay, this one I'm just going to let people read if you want to read it. This gives you a little bit more information about what does pKa tell you. pKa, I haven't really talked about yet. It's like you can calculate a pKa just like you calculate a pH. You take the negative log of your Ka. pKa of basis, the same thing. You can take the negative log of your pKb, and it will give your OH minus constant, or it'll give you your POH. And that's complicated. pH versus pKa. I don't think we're going to get into this much, but there's something you can read at your leisure. More. There's a different example. We're not going to worry about this one right now. I'm not teaching that. Okay.